Very good evening, students.
Good evening, sir.
Good evening.
Yes, good afternoon or good evening. Okay, so let us start with the discussion without wasting any time. Last class we have been discussing about collision theory, right? So the reactant molecules are colliding with each other to form respective products. In the process of collision, the reactant molecules will experience electronic repulsions. Because of those electronic repulsions, they should need some more energy, like the minimum amount of energy required to for the chemical reaction to occur is nothing but threshold energy. The minimum extra energy required by the reactant molecules to cross the energy barrier, that is said to be activation energy. So let us now study the same activation energy as well as threshold energy for the with the help of energy profile diagram for both exothermic as well as endothermic cases. First, let us consider exothermic reaction. Exothermic reaction means what? Delta H is negative. That means energy is released. That is enthalpy of product minus enthalpy of reactant. That was less than 0. So enthalpy of product is less than enthalpy of reactant. This is the first point. So we have progress of reaction. We have somewhere reactants here. And the reactants are going to be converting into products. The products will be having enthalpy somewhere down. So enthalpy of reactants and enthalpy of products, if you try to compare, enthalpy of reactants have high when compared to enthalpy of products. And then we have the energy difference between the reactants as well as the activated complex, that is activation energy for the forward reaction. For the backward reaction, the energy difference between products and the activated complex, that is activation energy for the backward. And from the x-axis to the activated complex, whatever we have, that is nothing but threshold energy. So enthalpy of reactant, enthalpy of product, if you try to compare, reactant has higher enthalpy when compared to product. Delta H is negative. That is activation energy for the backward reaction. Delta H is activation energy of forward minus activation energy of backward. So since delta H is activation energy of forward minus activation energy of backward, this is again found to be negative. Delta H is again negative from the graph, where with respect to activation energies also we can understand. HR is the enthalpy of reactant, HP is the enthalpy of product. Activation energy for forward, AF, activation energy for backward, EAB. The same thing we have understood previous class as well. Yes or no?
Yes.
Yes, right. So same thing. Now let us look at for a endothermic reaction. Endothermic reaction means what type of graph you will be expecting? You will be expecting a graph where the reactants are somewhere here and the products will have higher energy when compared to reactants. Somewhere here we have products. From the activated stage to the x-axis, whatever the energy we have, that is the threshold energy, and activation energy is difference between the activated complex and reactants. Products is like a difference between the energy of reactants, that is enthalpy of reactants, and enthalpy of products is delta H. That is found to be positive again because it is endothermic reaction. And product to reactant, what is the activation energy for the backward reaction? This is the activation energy. So EA of forward, this is EA of backward, and delta H is positive for the endothermic reaction. That is how we can understand the energy profile diagram for the endothermic case. Right, endothermic reaction means same type of graph whatever I have drawn. Reactants will be having less energy when compared to products. So products are at higher energy. So delta H is equals to enthalpy of product minus enthalpy of reactant, that is positive. Delta H you can also write as activation energy of forward minus activation energy of backward, that is also positive. And HP, HR, EAF, EAB, all of them have same meaning. Yes or no? If not specified in the question, then you have to consider EA as the activation energy for the forward reaction, not for the backward reaction. Is that clear or not?
Yes.
Yes, right. Factors affecting activation energy. What are the factors which will affect the activation energy? Nature of reactant. for different reactants, like reactant molecules are colliding with each other to form an activated stage. If I try to change the reactant, obviously the type of activated stage is going to be changed. What decides the energy of activated complex? The electronic repulsions in that stage. If the reactant molecules are changed, then the number of electrons present in that reactant molecules in the activated stage, that is different. So obviously the energy is going to be different. So nature of reactant, for different reactants, number of bonds and bond energies are different. Therefore, activation energy will also be different. Reactions which have less activation energy takes place at faster rate. Activation energy is the jump. Like all of you are doing a high jump, and I have kept a bar at 1 meter height. Only less number of students can pass it. If I kept the bar at 10 centimeter, most of you can pass it. Like it is the height or it is the jump. How hard, how far the bar is, less number of students can jump. Same way, how much higher the activation energy is, less number of reactant molecules can jump. Obviously, you will be having less product formation. The same you have studied with the help of Boltzmann, Maxwell-Boltzmann energy distribution. If you look at states of matter, gaseous states, there we have studied what, students? Like if you try to observe the Maxwell-Boltzmann distribution, on the y-axis we have fraction of molecules possessing a particular velocity. On the x-axis you have different types of velocities. Yes or no? Distribution of velocities.
Yes.
So on the y-axis you have fraction of molecules. On the x-axis you have velocity. And you will be having a curve like this. From this curve, what you can understand? From this curve, we have mentioned a point that the number of molecules possessing very low velocities or the number of molecules possessing very high velocities, they are less. Understand this point carefully. From the Maxwell-Boltzmann distribution of velocities, what we have understood is, if we take fraction of molecules on the y-axis and the velocity on the x-axis, the number of molecules possessing very low velocities is less. The number of molecules possessing very high velocity is also less. Now we don't know, there is some activation energy A. How much is that A? We don't know. What do we know from the graph? This is the maximum number of molecules possess what kind of velocity?
Most probable speed.
Most probable velocity. And then you have average velocity. This is most probable. And then you have average. And then you have
RMS.
RMS. Now let us say, with respect to UMP, you will be having a specific kinetic energy, because I have to talk with respect to energies. Because what I am saying, the molecules which can cross the activated stage, they can only reach the product formation when, if the orientation is proper. If the orientation is not proper, again after reaching the activated stage, they come back down. Now the question is, how much is the activation energy? We don't know. It will be some high energy. So with respect to most probable velocity, you will be having a particular kinetic energy, that is most probable kinetic energy. So I can also take the x-axis as kinetic energy axis, where for corresponding velocities I can calculate the corresponding kinetic energy using the formula kinetic energy is equals to half mv square. Using the formula kinetic energy is equal to half mv square, at every velocity I will be calculating the respect to kinetic energy and plot. Same type of curve I will be getting. Similar type of curve, not exactly same, because kinetic energy and velocities, they are going to be related by this function. Now what I can say is, somewhere we have activation energy here. This is your activation energy A. Because if I am taking kinetic energy in this x direction, somewhere you have activation energy, because energy axis I am talking about, somewhere the activation energy is there. This is your A point. So after this, whatever the number of molecules we have, all those molecules are said to be what? After this, there will be some set of molecules, right? Those set of molecules will be having energy greater than the activation energy. So they are called as active molecules or not? What are active molecules? Active molecules are those molecules which have a tendency. Active molecules are those molecules which have a tendency to convert to products. If the number of molecules, having energy greater than the activation energy are this much, those are called as your active molecules at a temperature, at a particular temperature T. With the increase in temperature, what happens? If I try to increase the temperature, what happened to the velocities? The velocities increase or not? URMS, UMP, average, all of them increase. Kinetic energy, what happened to kinetic energy? Kinetic energy increases.
Decreases.
What happened to the fraction of molecules?
Decrease.
Increases. With increase in temperature, the velocities increase, the kinetic energy increase, but the fraction of molecules possessing that velocity will decrease. So I can say this is a temperature T1, let us say. At a temperature T2, I have a curve like this. I'll draw a curve in this manner. Yes or no? Now what are my active molecules? This is your UMP now. Earlier your most probable velocity is here, somewhere here. That has been shifted now because I have increased temperature. So this is a temperature T2 and this was the temperature T1. At temperature T2, the number of molecules possessing most probable velocity will be less. But at temperature T2, you comment on the fraction of molecules. What is your activation energy? This is your activation energy. It doesn't matter what is the temperature. Activation energy has to be crossed so that the reactant molecules will be forming the products. This is still the activation energy. Activation energy is same. For the reaction, activation energy is same. But look at the number of molecules now, which has greater than activation energy. All these molecules are now the active molecules. Yes or no?
Yes.
Earlier, the number of active molecules are less, which has greater than activation energy. Now, with increase in temperature, the number of active molecules have been increased. That you can understand from the Maxwell-Boltzmann distribution of velocities as well. Okay. So, first one factor affecting the activation energy is the nature of reactant. With increase in temperature, what I can say? Number of molecules, number of active molecules increases. Activation energy is not changed. Understand this point. With increase in temperature, rate of the reaction increases. Why? With increase in temperature, rate of the reaction increases because number of active molecules increases. Not because the path has been changed. The path remains same. With increase in temperature, what happens? The number of active molecules increases because the number of collisions increases. But with increase in temperature, the activation energy and the reaction path, they are not changed. Presence of catalyst. What is the role of catalyst? Catalyst will try to increase the rate of reaction by decreasing
Decreasing
the
activity.
activation energy. So activation energy is going to be changed if you have a catalyst. Temperature is not changing the activation energy. Temperature is changing the number of active molecules. From the graph also you can observe at temperature T1 and T2 the same activation energy. Just the number of molecules has been increased. Presence of catalyst. Catalyst provides an alternate path. Like in the absence of catalyst, we have this curve. Somewhere we have reactants here. Somewhere we have products here. And in the absence of catalyst, we have this activation energy. In the presence of catalyst, we have a low path. This is activation energy in the presence of catalyst. This is activation energy in the absence of catalyst. In the absence of catalyst and in the presence of catalyst, the reaction path has been differed. Catalyst provides an alternate path of the reaction mechanism for the reaction. In the presence of catalyst, threshold energy decreases, activation energy decreases, and rate of reaction increases. Rate of reaction increases. Why? Because now the reactant molecules requires less energy to cross the energy barrier. In the presence of inhibitor is what? Inhibitor is nothing but a negative catalyst. Inhibitor will increase the activation energy, thereby increasing the threshold energy, thereby increasing the activation energy, thereby decreasing the rate of reaction. Catalyst is something which increases the rate of reaction. How? By decreasing the activation energy. Inhibitor is something which decreases the rate of reaction by increasing the activation energy. Are you understanding this point or not?
Yes, sir.
What happened to if I have a catalyst, is there a change in the enthalpy or is there a change in the Gibbs free energy or entropy? Try to answer this question. I am using a catalyst. For a reaction, I am using a catalyst. Is there a change in the Gibbs free energy or entropy or enthalpy? Entropy, enthalpy, Gibbs free energy Are they path dependent functions or state dependent functions?
State dependent.
Dependent function.
So even though I am changing the path, the reactant position and the product position are same or not?
Yes.
The reactants are there only. From the reactants only we are starting, and from the same products we are reaching. So even though I am changing the path, I have the same reactant and same type of product whose energies are same. So the change in the Gibbs free energy or the change in entropy or the change in enthalpy are not going to be deferred even though you use a catalyst. Only thing is, if you use a catalyst, the reaction occurs at a greater rate, that's it. But no change in the enthalpy or no change in the delta G or no change in the delta S, because entropy, Gibbs free energy and enthalpy are state functions. Catalysts do not change the enthalpy of reaction, free energy and entropy because they are state function. In the presence of inhibitor, threshold energy increases, activation energy increases, rate of reaction decreases. So this is how you can understand. This is a catalyst path. This is the absence of catalyst. Absence of catalyst means you have to have this much energy so that you can cross the hill. That means where the activation energy is highest. In the presence of catalyst, you can easily pass by lowering the activation energy. So everyone might be agreeing with this point because catalyst is something which lowers the activation energy, thereby increasing the rate of reaction. That is a very simple point to understand. And from this animation, you can easily understand it. But the question here is, how come a catalyst decrease the activation energy? On what basis you can say that catalyst is going to decrease the activation energy or inhibitor is going to increase the activation energy? Catalyst is going to decrease the activation energy by two perspectives. One is intermediate compound formation theory, other is adsorption theory. That will explain catalysis. Okay, surface chemistry is the next chapter. There will explain catalysis. Like how the catalyst is going to decrease the activation energy means, earlier we thought of this reaction, reactants converting into products. But now catalyst comes into picture, right? Catalyst will react first with reactants to form a different compound, which has less repulsions. Which has less repulsions means whose activated state will have less energy. And that will now convert to products. So it forms an intermediate compound. Intermediate compound formation theory means catalyst will actually form a different compound with reactants whose repulsions are less. Thereby that will convert to products easily. That is one theory. Second one is adsorption theory. Because of adsorption, the reactant molecules come and stick on the surface of catalyst. Thereby they form the products. Homogeneous catalysis can be explained by intermediate compound formation theory, and heterogeneous catalysis that will be explained by adsorption theory. Is that point clear?
Yes, sir.
Yes. We'll discuss that detail. The catalysis, homogeneous catalysis, heterogeneous catalysis, and details, promoters, catalyst, inhibitors, all those points we'll discuss in the surface chemistry. So this is the energy, this is a reactant, this is the absence of catalyst. In the presence of catalyst, what happened? The threshold energy decreased, the activation energy decreased. In the presence of inhibitor, what happened? The threshold energy increased, as well as the activation energy is also going to be increased. So more is the activation energy, less is the rate of reaction. Less is the activation energy, more is the rate of reaction. That is how you can understand the energy profile diagram in the absence of catalyst, in the presence of catalyst, and also in the presence of inhibitor. Right. Orientation. The first factor which we have understood so far is energy. The reactant molecule should possess energy so that they will collide. After collision, they will form the product formation. Now the orientation comes into picture. Proper orientation should be there, because orientation, if it is not there, the atomic orbitals will not overlap, because new bonds have to be formed. Like for example, let us say H2 plus I2 react to form HI. When the H2 molecule and I2 molecule collide, in the process of collision, the atomic orbitals of hydrogen and the atomic orbital of iodine will interact. That overlapping is nothing but the new HI bond. If the atomic orbital overlapping is not happening, obviously there is no bond formation. They will simply collide and disperse in different directions. You know how the billiard ball collide, right? One ball at the other ball simply collide at some random position, they disperse. So in the same way, the collision occurs. If the orientation is there, then only the activated stage can lead to the product formation. So this is how your reactant molecules are there. So reactants are colliding with the proper orientation. So you can just look at activated complex. In the activated complex, there is a proper orientation of atomic orbitals and they form the products AB. So AA, BB reacted to form AB. That is your proper orientation. Improper orientation, you can look at the animation. A and BB are colliding in this way. So this A atomic orbital and this B atomic orbital, they are not at all overlapping. There is no possibility of bond formation. So again, they will collide because they have energy, no? Because of the energy, they will collide. But since orientation is not there, they will again move in different velocities, remaining as A and BB only. That is, no products are going to be formed. Limitations of this collision theory. This theory is mainly applicable for gaseous reactions. You may ask a question, sir, why not for liquid reactions? Because the number of collisions happening will be great only for gaseous reactants. Because gases only will be having very high velocities because they have least intermolecular force of attractions. If I consider solid, two solids, if they are reacting, you cannot say based on collision theory the reaction is happening. Because the intermolecular force of attractions are strongest in solid 1 and solid 2. So reaction between them is not going to be easy. Same as liquids. This theory is mainly applicable for gaseous reactions and also for solutions in which reacting species are just molecules. Not a complex system, only bimolecular systems. This theory is mainly applicable for simple bimolecular reactions like H2I2 I have said, right? Simple bimolecular. You take an organic chemistry, organic molecule. A longer or larger organic molecule will never undergo a product formation as per this collision theory. In the total organic chemistry, we have never explained that the reactant molecules are simply colliding and leading to the product formation. We have a lot of chemistry, different perspectives are there. Yes or no? We have different electronic effects. Based on that only we'll comment on the product formation. It is not just because of collisions. Collisions will increase the rate. Higher temperature will increase the rate of reaction, that's okay. But not purely based on collisions. It considers molecules to be hard spheres. As I have told you yesterday also, the molecules will have a specific shape. That shape has been neglected or not? The shape of the molecule was never considered. Only they were considered as hard spheres, which is again incorrect. Some important points which you need to note. Activated complex is the most unstable complex formed in the transition stage with effective collision. If you try to look at the graph, reactants to product, which has the highest energy? This is the activated stage. Activated complex or activated stage has the highest energy, so that is the most unstable. Whichever has the highest energy, that won't be stable. If you have very high amount of energy, you won't sit at a particular position, you will move here and there. Same thing happens. Activated stage, activated complex will have highest energy, means it is unstable. According to Arrhenius, rate of reaction is directly proportional to e power minus Ea by RT. This is your Arrhenius equation we are going into. So K is equals to A into e power minus Ea by RT is nothing but your Arrhenius equation. So we'll discuss that. K is the rate constant, A is the Arrhenius factor. E power minus Ea by RT is nothing but the Boltzmann factor, where Ea is the activation energy, R is the gas constant, T is the absolute temperature. Rate of reaction is directly proportional to e power minus Ea by RT. K by A is the number of molecules possessing energy greater than activation energy. K by A, rate constant K divided by Arrhenius factor A, is the number of molecules possessing energy greater than the activation energy. We'll discuss that in the temperature factor. On increasing temperature, what happens? On increasing temperature, does activation energy changes?
No, sir.
No, we have explained the graph also. On increasing temperature, the number of active molecules, they are going to be increased. With the increase in the number of active molecules, the product formation increases, thereby the rate of reaction increases. But with increase in temperature, activation energy, that is not going to be increased. On increasing temperature, EA for reaction does not increase, but number of active molecules which are crossing the energy barrier increases, therefore rate of the reaction increases. So that is the scenario. Same graph, reactant to product, threshold energy. If you try to increase temperature, also same graph. Path is not going to be changed. Only thing is number of molecules having energy greater than activation energy will be high. Right? Try to solve this question. For the reaction, reactant converting into product, calculate the threshold energy, heat of reaction, activation energy of forward and backward reaction using following graph. Threshold energy, what is threshold energy?
100 kilojoules.
100 kilojoules, very good. What is activation energy of the forward? Activation energy of forward is
60.
40 to 100, right? Reactant and activated complex difference, 100 minus 40, that is 60 kilojoule. Activation energy of backward,
80.
100 minus 20, that is nothing but 80 kilojoule. And what else they asked? Heat of reaction, delta H is equals to
minus 20.
minus 20 kilojoule. It is nothing but activation energy of forward minus activation energy of backward, or enthalpy of product minus enthalpy of reactant. Delta H you can calculate as activation energy of forward reaction minus activation energy of backward reaction. Delta H you can also calculate as enthalpy of product minus enthalpy of reactant. Right? These are the values. For the endothermic chemical reaction, an endothermic chemical reaction is occurring in two steps as follows. A plus B is forming X, which is slow. X is forming AB, which is fast. The process of reaction can be best described by.
Fourth option.
First point is they said endothermic. But can you eliminate option 2? Because when compared to reactant, products are at lower energy. I can eliminate option 2. Can I eliminate option 3?
Yes, sir.
Yes, 2 and 3 have eliminated because endothermic they have said, but 2 and 3 are exothermic in nature. 1 and 4 are endothermic. Now look at, they have given the mechanism. A plus B is forming X, which is slow. A plus B is forming an intermediate X, which is slow, means, can I say, between this A plus B to X conversion, there is some transient state where the activation energy is highest.
Yes,
Because A plus B is occurring slowly. That means A plus B has to cross the very high activation stage. So where the A plus B to X, so can I say in the fourth option, the activation energy is highest when compared to first option.
yes.
You should not compare like this. You should not compare fourth option and first option. What you should compare is first activation energy and second activation energy. Like this is the A plus B to convert X, this much activation energy is required. X to AB is this much is required. So where the activation energy is highest? Within the same option. A plus B to X is highest, so it should occur slowly. X to AB is lowest, so it should occur fastly. So that is satisfying the condition. Go with the first option. A plus B to X is this much. X to AB is this much. So X to AB has higher activation energy in the first option. So but X to AB should be fast. So that is not going to be the correct one. Okay. You should not compare A plus B to X of first option and fourth option. You have to compare A plus B to X, X to AB in the same graph. Because A plus B to X slower and faster or lesser or higher among first and fourth option is all relative. Okay, you have to compare these lines given the same graph. Right. Next, factors affecting rate of reaction. We'll have nature of reactant, concentration of reactant, pressure of reactant. Pressure will be majorly only for consider for gases. Temperature, presence of catalyst, exposure to radiation. So these are the different factors which you will be considering to explain the rate of reaction. Nature of reactant to consider. First is physical state of reactant, where the rate of reaction is going to be highest.
Gaseous state.
Gaseous state. Why? For solid, liquid and gas, if you try to compare, where the collisions are greater. So obviously gaseous state. So increasing order of rate of reaction is solid least, then liquid, then gas. You can easily understand that in solid, the intermolecular force of attractions are greatest because of strong intermolecular force of attractions, they don't want to collide. So solid, liquid, and gas, if you try to compare, gases, because of least intermolecular force of attraction, they have greater tendency to collide. Yes or no? Because of greater tendency for the collision, they will optionally have a greater rate of reaction. So between three states, solid, liquid, and gas, gas highest, then liquid, then solid. Within the same states, like if I consider the same state now, if I consider solid state, within the same solid state, where the rate of reaction is going to be higher? Intermolecular attractive forces decreases, which provides more freedom for collisions. This is the same point. But if I consider two solids, that solid where the surface area is greater, there you will be having greater rate of reaction. Physical size of particle, if reactant is solid. Among solid, liquid, and gas, solid least, then liquid, and then gas, gas is the highest. If you are comparing two reactants which are already solids, then what you can say? Rate of reaction is inversely proportional to physical size or directly proportional to surface area. Rate of reaction is inversely proportional to physical size, directly proportional to surface area. You consider a cube. You consider one cube. What is the edge length of the cube? Let us say 1 meter. What is the total surface area of the cube? I have considered a cube where edge length is 1 meter. What is the total surface area of that cube?
6
6
square.
square.
6 meter square or 6, because 6 faces are there. Each face is a square. For a square, what is surface area? A square. So
A
edge
square.
length A is 1 meter. So 6 meter square. Now I am trying to divide that cube into, like I am dividing the cube in the x direction, in the y direction, and the z direction exactly half. How many cubes I am going to get? Like this room, you are just dividing this room in the x direction, y direction, and z direction. How many cubes you will get?
6 cubes.
Sure, Nandana? Like first divide this total cube into, in the x direction you divide, you will get 2 cubes. Again you divide those two in the exactly y direction, you will get 4. Again you divide, you will be getting what? 8 or not?
Yes, sir.
Try to think of the scenario. I am taking a cube, dividing into x direction, y direction, z direction. I'll be getting a smaller cube of edge length 1 by 2 or not? Now I'll be getting a smaller cube of edge length 1 by 2, but how many such smaller cubes I'll be getting? 8
Eight.
smaller cubes I'll get. So what is the total surface area now? We have total 8 cubes, 8 into surface area of each cube, 6a
1 by
square.
4.
So 6 into 1 by 2 into 1 by 2. How much is this?
12.
12.
12 meters square. Now divide it further. Divide this cube again into x direction, y direction, z direction. How many cubes you'll get?
8.
From every small cube of edge length 1 by 2, I'll be getting 8 more cubes. But how many small cubes are there of edge length 1 by 2?
8.
8 cubes already there. Every cube is giving 8 more cubes. So how many cubes I'm getting now?
16.
16.
64.
Sure.
64.
64.
We have 8 small cube students. Just imagine 8 small cubes are there. Every cube I'm dividing, I'm getting 8 more from every cube. From every cube of edge length 1 by 2, I'm getting 8 more cubes. So such cubes are 8. So 8 into 8, 64. So 8 power 2 cubes will get. So total surface area of the small cube of edge length 1/4 meter is, can I say 8 power 2 into, what is the surface area? 6 into 1 by 2 power 2 into 1 by 2 power 2. Can I write like this or not? Because edge length is 1 by 4 now. Can I say this as, I have divided the cube into 2 times. Then I get 8 power 2 into 6 into 1 by 2 power 2 into 1 by 2 power 2. Now I am doing the same division n times. I have taken a cube of edge length 1 meter. I have divided the cube in the x direction, y direction, z direction, got 8 cubes. Every small cube I am dividing again x direction, y direction, z direction. I am getting one more cube. Again I am dividing. Like that I am repeating the procedure for n times. So what is the total surface area? After n times, how many cubes I'll have?
8 to the power n.
8 to the power n into, obviously every cube will be having a total 6 faces. And what is the edge length of the cube? 2 power
1
n,
by 2 to the power n.
1 by 2 power n, and into 1 by 2 power n. So what is this? So this is nothing but your total surface area. Okay, it is not mathematics. I am trying to understand you what happens if you try to divide the cube. If you try to divide the cube of edge length 1 meter n times, this is the total surface area. The total surface area you can write in terms of 2 power 3n into 6. I am writing as 2 into 3 into 2 power minus 2n. So I can write this as like 6. I can write as 2 into 3, right? So the total surface area will be very high. So I can imagine this as 2 power 3 into 2 power n plus 1. You are getting or not?
Yes.
So if n is 10 times, imagine if n is 10 times, 3 into 2 power 10 plus 1. If n is 100 times, 3 into 2 power 100 plus 1, 2 power 101. You can imagine how high it is. So with the cutting a cube into half and half and half and half, and if you try to repeat this procedure up to 100 times, you are getting a extremely high surface area. If you make it a powder, just imagine how much the surface area will be. If you are taking a solid chunk and you are making it a powder, just imagine how much greatly the surface area has been increased. With the increase in surface area, how much greatly the rate of reaction increases, you can understand it. Right or not?
Yes, sir.
Yes.
Yes. So rate of reaction is inversely proportional to physical size and directly proportional to the total surface area. Then concentration of reactant. Concentration. Rate of reaction is just because of collisions as per collision theory. The reaction is happening because of collisions. More number of reacted molecules, more will be the collisions. Greater the number of reacted molecules, greater will be the number of collisions. Obviously, greater number of reacted molecules will be happening whenever concentration is high. So concentration of reactant and rate of reaction, they are directly proportional. Here we have few examples. Collision frequency will be low, the rate of reaction will be slower. On increasing concentration, what happens? More number of molecules are there, thereby you will be having higher collision frequency, thereby rate of reaction will be greater. Here we have many molecules, collision frequency will be high, the rate of reaction will be greater. Collision frequency will be high and the rate of reaction will be greater. Pressure. Effect of pressure on rate of reaction is negligible when reactants are in solid or liquid phase. For solids or liquid, pressure has no effect. But if the reactants are in gaseous state, then the rate of reaction increases on increasing pressure. From the top, if you are applying more pressure, more number of collisions are there, greater the number of collision, greater will be the rate of reaction. So rate of reaction increases on increasing pressure because number of effective collisions increases. That is only for gaseous reaction, not for solid and liquid reactions. So with increase in pressure, what happens? Greater will be the same number of molecules occupy lesser volume, so more number of collisions are there. Temperature. On increasing temperature, rate of reaction increases whether the reaction is exothermic or endothermic. It doesn't matter whether the reaction is exothermic or endothermic, rate of reaction increases. But as I have told you earlier also, the rate of reaction increases with increase in temperature, but the path of the reaction is same. On increasing temperature, kinetic energy of the molecules increases, number of activated molecules increases, number of collisions increases, thereby rate increases, but not by decreasing the activation energy. Okay, rate of reaction is increasing with increasing temperature because of increase in number of active molecules, but not because of decrease in activation energy. So you can just imagine the case where the temperature has been increasing slowly. With increase in temperature, how the molecules are colliding, you can see. And for every 10 degrees increase in temperature, the rate of reaction is found to be approximately double to triple. It will be increased by 2 to 3 times for every 10 degrees increase in temperature. So the effect of temperature you have to study with respect to two perspectives. One is Arrhenius theory and other is temperature coefficient. Relation between rate constant and temperature is explained by two methods. One is temperature coefficient mu. Mu is the ratio of rate constant at a T plus 10 degree divided by T degree. Mu is equals to KT plus 10 divided by KT. That is rate constant at T plus 10 degrees divided by rate constant at T. That is nothing but your temperature coefficient mu. Generally, it is found that for every 10 degrees rise in temperature, rate of reaction becomes 2 to 3 times. Generally, it is found that for every 10 degrees rise in temperature, rate of reaction becomes 2 to 3 times. It is defined as ratio of rate constant of reaction at two different temperatures having temperature difference of 10 degrees Celsius or 10 Kelvin. This is a function. Mu is equals to KT plus 10 by KT, and mu is found to be in the range of approximately 2 to 3. Whenever the value has been not given to you, you can consider it as 2. Whenever they have mentioned a value, then you have to take that value. Mu is equal to KT plus 10 by KT, that is approximately 2 to 3. If temperature of a reaction is not specified, then consider 25 degrees Celsius. If they have not mentioned any temperature, you have to consider room temperature. And if mu is not given, then you have to consider it as a minimum mu. Minimum of 2. Minimum mu is 2. Is that clear, students?
Yes.
Sir.
That's right. Try to solve this question. Temperature of reaction is 10 degrees. If the temperature increases by 50 degrees, then rate of reaction becomes how many times? 10 degrees, K1, let us say. 10 to 20 degrees, how much it is? 2 K1. 20 to 30 degrees, 2 power 2 K1. 30 degrees to 40 degrees, 2 power 3 K1. 40 to 50 degrees Celsius, 2 power 4 K1. 50 to 60, 2 power 5 K1. Increased by 50. So 10 to 60, how much is the difference? Delta T is equal to 60 minus 10, that is equal to 50. So increased by 50 degrees means, so you have to increase temperature by 50 degrees. Increase to 50 degrees means you have to stop it here. If the temperature increases to 50 degrees means you have to stop it here, then you will be having 2 power 4 K1 only. Temperature increases by 50 degrees means you have to proceed till here, then you will have 2 power 5 K1. So rate of reaction will be 2 power 5, 32 times that of K1, initial rate of the reaction. The same constant, K is equals to KT plus 10 by KT, that is equals to 2 to 3. And here you have R2 by R1 is equals to K at a different temperature T2 divided by K at a temperature T1 is equals to mu power delta T by 10, or K2 is equals to K1 into mu power delta T divided by 10. K2 is equals to K1 into mu power delta T divided by 10. This is your rate constant at temperature T2. Rate constant at temperature T2 is equals to rate constant temperature T1 into mu power. Mu is the temperature coefficient. Mu power delta T by 10. This is a function, or this is a formula used to calculate rate constant at different temperature. Whenever mu value is given to you, other than 2, if the mu value is given, then you have to use this relation. Is everything clear so far?
Yes, sir.
Sir.
Yes.
Right. Try to find out this. Find out K40 by K25 for a chemical reaction. K40 divided by K25 is equals to mu power delta T by 10. What is delta T? Delta T is nothing but 40 minus 25, that is 15. Mu, do they mention the value of mu? Mu value has been not mentioned. So whenever mu value is not mentioned, you have to consider as to delta T is not just a 10. If it is 10, you can say double, but it is 15 now. So you have to use this formula. So K at 40 divided by K at 25 is equals to mu is 2, 2 power, delta T is 15, 15 divided by 10. That is 2 power 3 by 2. 2 power 3 by 2 is 2 root 2. 2 root 2 is yes or no?
Yes, sir.
Yes,
2.8.
2.82. Approximately 2.82. Rate of reaction increases 5.19 times when temperature increased from 40 degrees Celsius to 3 degrees Celsius. If mu of the reaction is 3, find out 3 degrees Celsius. 40 to 3 degrees, mu is 3. So R2 by R1 is equals to K2 by K1. That is equals to mu power delta T by 10. Rate of reaction increased by how many times? 5.19 times R1 divided by R1 is equals to mu is 3. 3 power delta T is how much? Delta T is 40 to T means T minus 40, right? Increased from 40 to T. So T minus 40 divided by 10. R1 gets cancels out. So 5.19 is equals to 3 power T minus 40 divided by 10. Logarithm you can apply. Logarithm of 5.19 is equals to T minus 40 by 10 logarithm of 3. So T you can calculate here. T is equals to 10 times of logarithm of 5.19 divided by log 3 plus 40. Okay, this is your T in degrees Celsius. If you have any difficulty directly writing, you can write down in many steps. So 10 times of logarithm of 5.19 is equals to T minus 40 into log 3. 5.19 you can approximate to 5.2. Yes or no? 10 times of logarithm of 5.2 is equals to divided by log 3 is equals to T minus 40. Therefore, T is equals to 40 plus 10 times of logarithm of 5.2 divided by log 3. Substitute it. You can calculate the approximate value of log 5.2. Then you will be getting the right answer. Is that clear?
Yes, sir.
Yes. Maxwell and Boltzmann energy distribution curve. This was the same curve which I have discussed earlier. If you try to take fraction of molecules on the y-axis, kinetic energy on the x-axis, this is the fraction of molecules at temperature T. This is the most probable kinetic energy. So earlier we have plotted a graph with velocity, but with respect to activation energy, we have to comment, right? So that's why now I am changing the velocity to respect to kinetic energy. So at every velocity, this is the most probable velocity. There I have calculated the most probable kinetic energy. So let us say this is somewhere your activation energy. These are the fraction of molecules which have energy greater than the activation energy. That means these are the fraction of active molecules at a temperature T. If you try to increase temperature, what happens? If you try to increase temperature, you will be having this fraction, because with increase in temperature, like T plus 10, if you take, with increase in temperature, the fraction of molecules possessing more energy than the activation energy will be high. So with increase in temperature, what you can say, students, the number of active molecules increased, but the path is same, but the energy profile diagram, reactants to product conversion is same. Relation between rate constant and temperature is explained by following two methods. In that first method we have seen temperature coefficient method, and second method is Arrhenius equation. What is Arrhenius equation? K is equals to A into e power minus EA by RT. What is K? Rate constant. What is A? Arrhenius factor. Arrhenius factor gives idea about the number of collisions happening. What is e power minus Ea by RT? That's the Boltzmann factor. K is equals to A into e power minus Ea by RT. K is the rate constant. A is the Arrhenius constant or pre-exponential factor. This is exponential, pre-exponential factor or frequency factor. Ea is the activation energy. T is the absolute temperature. R is the universal gas constant. R is the gas constant. T is the absolute temperature. Unit of A and unit of K. K and A will have same units. Same units. Why? Because e power minus Ea by RT, that is the exponential which is not having any units. And what is K by A? K by A is equals to e power minus Ea by RT. What I have told you earlier, K by A. Anyone remembered? K by A.
Molecules increases.
Value of K increases with increase in temperature. That you can understand. If temperature goes to infinity, what happens then? If temperature goes to infinity, then K will be equal to A. Yes, Dimple, very good. Molecules with a higher energy than the activation energy. Very good. K by A is the number of molecules which has energy greater than the activation energy. K by A is equals to e power minus Ea by RT. K by A is nothing but the fraction of molecules having energy greater than activation energy. This point you have to understand. Because some questions can be asked where they'll be giving percentage of active molecules. So in a molecular system, these many percentage of molecules are active in nature, like 10%, 20% like that. That means they have given the K by A value. You have to understand that. And from there, you have to solve it. E power minus Ea by RT is nothing but Boltzmann factor. On taking logarithm in equation 1, so K is equals to A into e power minus Ea by RT. So you can take ln K is equals to ln A minus Ea by RT. So you can convert this natural logarithm to log to the base 10. So 2.303 log K to the base 10 is equals to 2.303 log A to the base 10 minus Ea by RT. So log K to the base 10 is equals to log A to the base 10 minus or plus of minus Ea by 2.303 R into 1 by T. So log K is equals to log A plus of minus Ea by 2.303 R into 1 by T. If you try to plot a graph between log K versus 1 by T, log K you are taking on the y-axis, 1 by T you are taking on the x-axis. Y is equals to mx plus c. What will be the slope? Log A will be the y-intercept. What will be the slope? Slope will be is equals to minus Ea by 2.303 R. Ea and R both are positive, so slope is negative. So tan theta, theta should be belonging to quadrant 2. Log K versus 1 by T, if you try to plot a graph, you will be getting slope is equals to minus Ea by 2.303 R. Sometimes they will plot a graph between ln K and 1 by T. Whenever they are plotting between ln K, you won't be getting 2.303. You will simply get minus Ea by R. Whenever the plot is graph between ln and 1 by T, you will simply get minus Ea by R. 2.303 you will not get, right? Ea of the reaction can be determined by measuring rate constant two different temperatures, because log K is equals to log A minus Ea by 2.303 R T1. This is the K1, that is rate constant temperature T1. Log K2 is log A minus Ea by 2.303 R T2. when I try to take the when I try to subtract this, log K1 minus log K2 is equals minus EA by 2.303 R into 1 by T1 minus 1 by T2, because minus of minus become plus. So logarithm of minus, if I take to the other side, it becomes minus log 1 plus log minus log K1 plus log K2. That is logarithm of K2 by K1 is equals to EA by 2.303 R into 1 by T1 minus 1 by T2. Logarithm of K2 by K1 is equals to EA by 2.303 R into 1 by T1 minus 1 by T2. So if rate constant at one temperature is known to you and the two temperatures are known to you along with activation energy, you can calculate the rate constant at different temperature. Yes or no? This was a relationship between rate constant at two different temperatures. If you know rate constants at two different temperatures, you also know temperatures, then you can calculate activation energy also. Is it clear to everyone?
Yes, sir.
Yes, sir.
Yes, Varshita, everyone says clear now. You should ask a question like, sir, you said A is the collision frequency, but A you are taking same. Why? That is the approximation we have taken. A, what is A? A is a collision factor or not? What we have told you? A is the Arrhenius constant or pre-exponential factor or frequency factor, collision frequency factor. So I am changing the temperature. I am changing the temperature. So with change in temperature, the number of collision changes or not? But still I am taking same A, log A, log A. So that A, the change in A with change in temperature was neglected. Okay, at two different temperatures also, A is assumed to be a constant. Arrhenius factor was assumed to be a constant. That is an assumption. At temperature T1 and temperature T2, you have the same equations, whatever we have written. Log K2 by K1 is equals to EA by 2.303 R into 1 by T1 minus 1 by T2. And we can also do the differentiation. K is equals to A into e power minus EA by RT. You can write the same equation as ln K is equals to ln K is equals to ln A minus EA by RT. A is a constant with respect to temperature. Constants or with respect to temperature. That means even though I try to change temperature, A is not changing. So with respect to that knowledge, can I do the differentiation now? Differentiate this with respect to temperature. So d by dt of ln K is equals to d by dt capital D temperature with respect to temperature. I'm doing the differentiation of ln A minus d by dt of EA by RT. Yes or no? We got this equation or not? D by dt of ln K is equals to d by dt of ln A minus d by dt of EA by RT. So K depends upon temperature, so I cannot do anything. A will it depend upon temperature? A is constant with respect to temperature. So what is d by dt of ln A?
Zero.
Zero.
It goes to 0. What is EA? EA is activation energy. Is that going to be depending upon temperature or not?
No, sir.
That we have said many times that activation energy is not going to be changing even though you change temperature. What is changing? What is changing even though you change temperature?
Number of active molecules.
Active molecules. So EA is a constant. So R is a universal gas constant. So EA and R, can I take out of d by dt? So d by dt of ln K is equals to minus EA by R. Since EA and R are constants, then only I can take it out. If they are not, if EA depends upon temperature, I could not take it out of the d by dt. Okay, so minus EA by R, d by dt of 1 by t. What is d by dx of 1 by x?
Minus 1 by t square.
Minus 1 by t
Minus
square.
1 by t square. Minus into minus become plus. So d by dt of ln K is equals to plus EA by R t square. This is also other form, differential form of Arrhenius equation. What is this? Differential form of Arrhenius equation. The same Arrhenius equation, but in the differential form. d by dt of ln k is equals to EA by RT square. Yeah, this is what we are talking about. d by dt of ln k is equals to EA by RT square. This is nothing but differential form of Arrhenius equation. So since EA is not depending upon temperature, we are taking out of the differentiation, and ln A is a constant. It is not changing with respect to temperature. So differentiation of a constant is 0. So like that you get this equation, right? The same equation which we have derived in the last slide. Next, what is the other factor which is going to be changed with a like rate of reaction is also going to be depending upon catalyst. With increase in, like if we take a catalyst, the activation energy is going to be decreased, thereby increasing the rate of reaction. If we take an inhibitor, activation energy, threshold energy will increase, thereby decreasing the rate of reaction. In the presence of catalyst, EA of the reaction decreases and hence rate of reaction increases. Exposure to radiation. Rate of some reactions also increases when reactions are carried out in the presence of radiation, only for photochemical reactions. Example you can consider formation of HCl. H2 plus Cl2 gives 2HCl. It is a very slow reaction. H2 plus Cl2 gives us to HCl is a very slow reaction. H2 plus Cl2 gives us to HCl. In the presence of sunlight, this reaction will be happening at a greater rate. What we can say is, in the presence of radiation, the bond between two hydrogen atoms can be broken easily. The bond between two hydrogen atoms is a strong bond or a weak bond?
Strong bond.
Strong bond.
Why?
Due
Between
to
two
minus
hydrogen
minus
atoms, we
over.
have 1s overlapping. 1s is the smallest atomic orbital. The smallest atomic orbitals will overlap to a maximum extent. Greater the extent of overlapping, greater will be the strength of that bond, because of stronger bond H2 and Cl2 forming 2HCl. So this will happen in the presence of sunlight. So what is going to happen to this reaction? The rate of this reaction is going to be increased in the presence of sunlight. Right, these are the different conditions affecting the rate of reaction, or different factors which are affecting the rate of reaction. Try to solve some examples. For a first order reaction, calculate the value of pre-exponential factor. Pre-exponential factor means A, and activation energy, that is EA. You have to calculate activation energy in kilocalories in the following equation. Log K is equals to 6 minus 2000 by T. We know this equation. Log K is equals to log A minus EA by 2.303 RT. So what is log A? Try to compare. Log A is equals to 6.
minus
So what is A?
10 to the 6.
10 to the power of 6. And what is minus EA by 2.303 R is equals to minus 2000. So EA is equals to 2000 into 2.303 into R value in terms of calories you write down.
2.
2 calories, Kelvin inverse, mole inverse. Yes or no?
Yes, sir.
So EA you try to calculate 2000 into 2.03 into
4606 into 2.
4.606 into 2.
Sir, 4606, no, sir. This 1000 and this 3 point.
Because kilocalories, no.
Okay, sir.
Okay. 2 into, like 4 into 2.303. 4 into 2.303 kilocalories. So this will be your respective EA. Right?
9.21.
Okay. 9.2 approximately.
Sir.
Yes, right. Try to solve this question. The value of rate constant is doubled when temperature is increased from 27 degrees Celsius to 37 degrees Celsius. Calculate the value of activation energy in kilojoules. So we have the equation logarithm of K2 by K1 is equals to EA by 2.303 R into 1 by T1 minus 1 by T2.
By T2.
Yes or no? So logarithm of rate constant doubled. So 2K1 by K1
by K1
is equals to EA by
2.303
2.303 into R into 1 by T1. What is T1? 300,
300
400.
310.
310
So log 2 is equals to EA by 2.303 R into 310 minus 300 divided by 310 into 300. Therefore, EA is equals to log 2 is 0.3010 into 2.303 into R in kilojoules they want. So 8.314 I am writing. So I am getting in joules into 300 into 310 divided by 10. These many joules. So EA is equals to 1 times 10 times cancels out. So 0.693 into 8.314 into
310 into 30.
3.1 into 3 kilojoules. Can I write like this? By 1000 I have to do, no? If you have difficulty, write again. 310 into 3 in 310 into 30 divided by 1000 kilojoules. 0 gets cancels, 0 gets cancels. 31 by 10 is 3.1. So EA is equals to 0.693 into 8.314 into 3 into 3.1 kilojoules. These are the respective value of activation energy in terms of kilojoules. Clear or not?
Yes, sir.
Yes. This calculation part you have to do and report your answer. For elementary reactions A to B, K1 is equals to 10 power 15 into e power minus 2000 by T. K2 C to D, K2 is equals to 10 power 14 into e power minus 1000 by T. Calculate temperature at which rate constant of both the reactions are equal. Two reactions they are given. You have to find the temperature at which rate constants are equal. So solution goes like this. So K1 is equals to K2. That's what they mean. So what is K1? 10 power 15 into e power minus 2000 by T is equals to 10 power 14 into e power
minus 1000 by
1000 by T. Can I say 10 power 14, 10 power 15 cancels out and
10.
we left out 10.
E
10
power
into e power minus 2000 by T is equals to e power minus
1000
by T. So I can take this e power minus 2000 by 2 the other side. I can write e power minus 1000 by T into e power plus 2000 by T.
2000 by T.
So 10 is equals to e power 1000 by T. So apply logarithm, natural logarithm. ln 10 is equals to ln of e power
E power
1000 by T. So ln 10 I can write as 2.303 into log 10 is equals to ln e.
2.303.
No, ln e is there, right? 1000 by T you can
Yes.
directly write. Yes or no?
Yes.
So 2.303 into log 10 is 1 is equals to 1000 by T, or temperature T is equals to 1000 by 2.303 Kelvin. So this was the temperature at which you will be having the rate constants of both the reactions. They are going to be equal. Yeah, Faizan says 434.2. You can just look at the calculation. Yes.
Yes, at 434 point.
Yes. Try to solve this question. If chemical reaction occurs in 3 steps, having rate constants K1, K2 and K3, the overall rate constant of reaction is K is equals to K1, K2 by K3. EA of first, second and third steps are 30, 40 and 60. Determine the overall active exchange of the reaction. Yes, Arshia also says 434.21. Very good. Try to solve this. If chemical reaction occurs in 3 steps, rate constant are K1, K2, K3. The overall rate constant of reaction is also given K1, K3 by K2. So can I say K is equals to A into e power minus EA by RT. So wherever I have K1, there will have activation energy as EA1. So K1 is equals to A into e power minus E1 by RT. K2 A into e power minus E2 by RT. K3 is equals to A into e power minus E3 by RT. So activation energy K is equals to K1 K3 by K2. That is equals to K is equals to A into e power minus EA by RT is equals to K. K is nothing but for the overall reaction, let us say activation energy is EA. That is equals to A into e power minus E1 by RT into A into e power minus E3 by RT whole divided by A into e power minus E2 by RT. A gets cancels out. A here gets everything cancels out. So e power minus EA by RT is equals to e power minus 1 by RT into E1 plus E3 minus E2. So therefore, activation energy of the new reaction is E1 plus E3 minus E2. So what is E1? 30. What is E3? 60. E2 is 40. So 90 minus 40, 50 kilojoule per mole. This is the activation energy of the new reaction whose rate constant is actually given by K1, K3 by K2. Got it or not?
Yes, sir.
Okay. Try to solve this problem. At 500 Kelvin in a reaction, 0.001% of the total molecules are active molecules. Calculate activation energy EA in the kilocalorie per mole. The unit has been given as kilocalorie per mole. All of you try to solve this question. I'll be back within a minute. Yes, students, anyone got the answer? The Faizan says 11.515. Let us try to solve it. At 500 Kelvin, in a reaction, 0.001% of total molecules are active molecules. So as I have told you, So from the Arrhenius equation, K is equals to A into e power minus EA by RT. You can rearrange the same equation as K by A is equals to e power minus EA by RT. K by A is equals to e power minus EA by RT. This K by A is nothing but, what is this K by A? Fraction of molecules.
Lossless
Yeah,
greater energy greater than activation energy.
very good. Fraction of molecules with energy greater than or equal to activation energy. That means these are nothing but active molecules. That is, these are active molecules. What they are saying, at 500 Kelvin in reaction, 0.001% of the total molecules are active molecules. That means K by A is nothing but, how many active molecules are there? 0.001 divided by 100, since they are talking about percentage. So 0.001 by 100 is how much? 10 power
-5.
minus 5. So 10 power minus 5 is equals to e power minus EA by RT. EA we have to calculate, divided by R into temperature is given 500 Kelvin. Everything is given, just substitute. Ln of 10 power minus 5 is equals to minus EA by R into 500. So minus 5 into 2.303 into log 5 is equals to minus EA by R into 500. So minus minus gets cancels out. So log 5 you can write as log 10 minus log 2, or you can directly substitute 0.69. So there you can calculate the activation energy EA as in terms of kilocalories. So R you can write as 2 divided by 1000 kilocalories into 500 into 2.303 into log 5 you can write as 0.69 approximately. This is the value of activation energy in terms of kilocalorie, and check out the answer, 11.5 approximately. Is that true? Everyone has to check.
1 point.
Sir,
Log 10, sir.
sir,
Log
that
10.
would be log 10. You
Yeah,
have
log
written log
10.
5 there.
Yeah, log 10, log 10. Log 10, it is 1, right? Yes. Yeah, this 5 we have taken out, right? That's why we have mistakenly written. So 5 minus 5 into ln 10. ln 10 is nothing but 2.303 log 10. Is that clear, students? Is everything clear so far?
Sir, then answer should be
Check out answer. Okay, answer I have not calculated. Whatever the answer given here in
2.303 calculated.
answer is how much? How much you are getting? Answer, you check it out.
2.303, sir.
Sir, that is you have written 5 by 2 by 1000. That is 5 by 1000, right?
5
Uh,
into
5 by
5 by
1000.
1000.
Hmm. That's what you check out the calculation. Okay. 5 in 5
5
into
by 1000.
yes.
5 by 1000.
That will be 11.5, sir.
Yes. Ultimately, we have R value have written 2 by 1000 kilocalories into 500 written 2.303 into 1 into 5. I have to write extra. 2.03 written. Log 10 is 1. 5 we have written. R value I have written 2 by 1000 kilocalories 500. So this value we try to calculate. Okay.
11.5.
Yes.
11
11
point.
point. Right. So this is all about your chemical kinetics. You have to solve a lot of problems. So let us start with the next chapter, named surface chemistry. Just a second. surface chemistry, in surface chemistry we'll have 3 points majorly, like 3 topics majorly to discuss. Like what is surface chemistry? First of all, if you try to understand, surface chemistry is a branch of physical chemistry which deals with the study of physical and chemical phenomena that occur at the interface of two phases. Wherever you have interface of two phases, at that interface of two phases, whatever the physical and chemical phenomena happening, whatever the study we are doing regarding the interface of two, at the interface of two phases, that is nothing but your surface chemistry. We will study both the physical phenomena as well as chemical phenomena. So in the surface chemistry, what are the points we are going to cover is adsorption, colloids, and catalysis. In the adsorption, we'll talk of the what is adsorption, chemistry of adsorption, and what are different factors on which adsorption depends upon, and adsorption as the Friendlich adsorption as the Langmuir adsorption as the colloids. We will be studying about classification of colloids based on the physical state of dispersed phase and dispersion medium, based on the type of affinity between dispersion medium and dispersed phase, based on the type of particles like multimolecular colloids, macromolecular associated, micelle formation, CMC, Kraft temperature, purification, dialysis, electrodialysis, ultrafiltration, preparations of colloids, lyophobic colloids, oxidation, reduction, double decomposition, hydrolysis. We will talk about properties of colloids, colligative properties, filterability, optical properties, Tyndall effect, color, visibility, charge, adsorption, electrical double layer, zeta potential. We'll look at the coagulation, principles of coagulation, how the coagulation will occur, boiling, adding oppositely charged colloids, flocculation values, coagulating values, protection of lyophobic colloid by lyophilic colloid. There we have gold number and concept. Then we'll discuss about emulsions, oil in water type, water in oil type, colloids around us, delta formation, blue color of the sky, applications of colloids, medicines, tanning, electrical precipitator, quartal precipitator. Then the third characteristic is catalysis, homogeneous catalysis, heterogeneous catalysis. Different properties like catalyst, poison, promoter, inhibitor, enzyme catalysis, zeolites, shape selective catalysis. So these are the overall discussion, overall points of discussion which you are going to cover in the adsorption, in the colloids as well as in catalysis. Is that clear or not? That is the points of discussion. Since you have already studied earlier, just I am overviewing what we are going to look in this particular chapter. Right? So adsorption, if you go with the definition, the accumulation of molecular species at the surface rather than in the bulk of a solid or liquid due to molecular surface forces, that is called as adsorption. Due to molecular surface forces, the accumulation of other molecular species on the surface, that is called as adsorption. And the species on which adsorption occurs, that is called as what?
Adsorbent.
And the species which is getting adsorbed, that is called as
Adsorbate.
adsorbate. The substances, solids, liquids, or gases which are adsorbed on the surface of adsorbents, they are called as adsorbate. The solid or liquid substance on the surface of which adsorption takes place, that is said to be adsorbent. Examples of some commonly used adsorbents, that means on whose surface adsorption is going to happen, is like palladium, silica gel, activated charcoal, starch, gum arabia, egg albumin. So on all these surfaces, you can see the phenomena of adsorption occurring. Mechanism of adsorption, if you try to observe, what was the mechanistic approach of adsorption? You consider any surface of any solid. On the surface point, we have unbalanced force or not?
Yes, sir.
There are always unbalanced forces present on the surface points. What is going to happen is, because of the presence of unbalanced forces on the surface, the gas molecules which are present above that particular surface, they can develop new interaction with the surface to balance these unbalanced forces. Every surface point is under some tension. So can I say the surface, since every point of the surface is under tension, can I say surface will have some energy, and that is called as surface energy.
Yes.
And because of adsorption, that surface energy is lost. The surface energy is lost in the form of what? Heat. So in the process of adsorption, like if I consider any solid, like this is a solid, imagine on the surface you have unbalanced force. Why? Because the molecule inside the bulk is surrounded by equal forces in all the directions, whereas molecule on the surface only has force of attraction in the downward direction. So net force of attraction on the molecule on the surface is down. But can the molecule on the surface can go into the bulk?
Yes.
No, it can't go because of immediate repulsions. So on the surface, we have surface energy. Because of adsorption of some gas or adsorbate on the adsorbent, the surface energy is lost in the form of heat. So delta H is
Negative.
negative. And what happened to delta S? Change in entropy.
Decreases.
Delta S of system is negative or positive? Negative. Why?
Negative.
Because the random movement of the molecules has been decreased. But what happened to delta S total? Delta S total is always positive.
Increased. Positive.
Delta S total is nothing but total entropy change of the system. The entropy of the system plus entropy of the surrounding, that should always be positive. From that only we say delta G has been obtained, which should be negative. So delta G is equals to delta H minus T into delta S. Delta G is equals to delta H minus T into delta S. So delta G will be negative at lower temperatures or higher temperatures, because delta H is negative, minus T into delta S is
Lower.
also negative. So delta G is negative at lower temperatures. As you try to increase temperature, what is going to happen? As temperature increases, adsorption decreases. Adsorption decreases. Why? Because delta G will become positive. That is a thermodynamic aspect. But what we can say in other terms, as temperature increases, I am just saying that temperature increase means adsorption decreases. That is the overall perspective, but it differs for physisorption and chemisorption. For chemisorption, what happens with increase in temperature? Adsorption. Chemisorption. For physisorption, with increase in temperature, physical adsorption decreases. But chemical adsorption first increases and then decreases. Chemical adsorption first increases and then decreases, because chemical adsorption means a chemical bond has to be formed between the adsorbate and the adsorbent. Whatever the increase in temperature you're doing, that serves as an activation energy to break the bond between the adsorbate atoms. In the adsorbate, we have two atoms, right? Between the atoms, we have bonds. Those bonds have to be broken and new bond have to be formed. New bond has to be formed. So with increase in temperature, in the chemical adsorption, first the extent of adsorption increases and then decreases. But in physical adsorption, with increase in temperature, physical adsorption decreases. Okay. So delta G is equals to delta H minus T into delta S. This is a surface energy. On surface, whatever the points you have, that leads to surface energy is lost in the form of heat. Delta H is negative. Delta S of system is negative. Delta S total is positive. Negative minus of T into negative. Delta G should be positive. Delta G should be negative for spontaneity. Right? Mechanism of adsorption. So this was the bulk molecule which has equal force in all the directions. Now consider the surface molecule which has net downward force. So gas molecules has a tendency to now unbalance to balance the unbalanced forces. So they will now come and stick on the surface. So particles inside the adsorbents are completely surrounded by other particles on all sides. Hence the intermolecular forces are mutually balanced. Particles at the surface of adsorbent are not surrounded by atoms or molecules on all sides. Hence they possess unbalanced or residual attractive forces. On the surface, whatever the particles we have, they are not completely balanced. These forces of the adsorbent are responsible for attracting the adsorbate particles on its surface. These forces of the adsorbents are responsible. These forces of adsorbents are responsible for attracting the adsorbate. The adsorbate particles are attracted because there is an unbalanced force. Adsorption is an exothermic process because surface energy is lost, delta H is negative. Freedom of movement of gas molecule decreases, delta S of gas is negative. Adsorption is an spontaneous process, so delta G is negative and delta S total, that has to be positive. Delta S total is always positive, delta G has to be negative. Then only the process is said to be spontaneous in nature. When delta G is equals to negative, state of equilibrium is attained. Delta G is equals to negative at equilibrium, but delta G naught is not equal to 0 at equilibrium. At equilibrium, only the condition is delta G has to be negative, but not delta G naught. Yes or no? So that's the particle. On the surface, you have seen the adsorption. When a substance is uniformly distributed throughout the body of a solid or liquid, when a substance is uniformly distributed throughout the body of a solid or liquid, the phenomena is called as absorption. Absorption means uniform distribution is there. The process in which adsorption and absorption takes place simultaneously. Adsorption happening, absorption is also happening. Then that is said to be sorption. Desorption means what? The process of removing the adsorbed substance from the surface on which it is adsorbed. D means removal, right? Desorption means removal of adsorbed substance from the surface. And adsorption of gases on metal surface, that is said to be occlusion. So whatever the discussion we have studied in the hydrogenation of alkenes to form alkanes, alkene and H2 both are in the gaseous phase, they are adsorbing on the respective metal. So that is nothing but your occlusion. Adsorption of gases on the metal surface, that is said to be occlusion. Desorption means removal of adsorbed surface, removal of adsorbed substance from the surface. Sorption means in which adsorption and absorption takes place simultaneously. Absorption means when a substance is uniformly distributed throughout the body of a solid or liquid or gas. Right? Difference between adsorption and absorption. Adsorption means what, students? Adsorption means it involves higher concentration of the gas or liquid at the surface. Absorption means uniform distribution of molecular species throughout the bulk. Absorption means throughout the bulk you have the molecules concentration will present. Adsorption means only on the surface. Adsorption is it is rapid in the beginning and slows down near the equilibrium. Absorption occurs at uniform rate. Why it is so? Why the adsorption is rapid in the beginning and slows down near equilibrium?
Because surface decreases as time proceeds.
Yes, obviously, as the time is proceeding, the surface area available for adsorption is decreasing. Adsorption purely depends upon the surface area. Greater the surface area, greater will be the adsorption. Because of unbalanced forces only, the adsorption is happening. Okay, so it is beginning in the, it is rapid in the beginning and slows down near the equilibrium, whereas absorption occurs at uniform rate. Adsorption is a surface phenomena. Absorption is not a surface phenomena. It occurs throughout the body. Adsorption is a fast process. Absorption is a slow process. Why? Because in adsorption there was a driving force. The unbalanced forces present on the surface, they are attracting the unbalanced forces present on the surface, they are attracting the adsorbate molecules. So there was a driving force. But in absorption, no driving force. The uniform rately, at the uniform rate, the absorption will occur. Is everything clear so far?
Yes.
Yes, right. Adsorption. When charcoal is mixed with methylene blue, its blue color is adsorbed or adsorption by charcoal and the dye. Blue color is going to be adsorbed. That is adsorption occurred. Adsorbed by charcoal and the dye becomes colorless. What happens when charcoal is mixed with methylene blue? Its blue color is adsorbed by charcoal. Whatever the charcoal is there, that is actually absorbing the blue color of the methylene blue. Thereby, dye becomes colorless. When charcoal is mixed in yellow sugar, yellow colored sugar solution, then yellow color is adsorbed by charcoal and white colored sugar solution is obtained, which is nothing but adsorption, which is again a phenomenon of adsorption. So charcoal is an adsorbent, methylene blue color, and the yellow colored sugar solution, they are actually adsorbates. In both the scenario, adsorbent is charcoal. In both the scenario, adsorbent is charcoal. Right? Types of adsorption: physical adsorption as well as chemical adsorption. There are two types of adsorption: physical adsorption, chemical adsorption. In physical adsorption, what is going to happen? In physical adsorption, the adsorbate molecules will develop just a van der Waals force of attraction with the adsorbent surface. Whereas in the chemical adsorption, the adsorbate and adsorbent, they are going to form new bonds. Physical adsorption also called as physorption. Physical adsorption, if you look carefully, it is unimolecular or multimolecular.
Multimolecular.
Why? You have to know why, right? Why it is multimolecular physical adsorption? Because there is no orbital overlapping. It is just the van der Waals force of attraction, like dipole force, like unbalanced force attracting the gaseous molecules. There is just a van der Waals force of attraction between the adsorbents and adsorbates. There is no orbital overlappings involved. So that attraction can be with anyone. Bonding is different, attraction is different. Yes or no? This, because of that attraction, it will lead to the multimolecular. Chemisorption is mostly unimolecular. It is caused by intermolecular van der Waals forces. So it is not specific. It is not going to be specific. It is reversible. Why it is reversible? Because the adsorbed gas molecules can easily dissolve because the van der Waals force of attractions are weaker. And the heat of adsorption, how much amount of heat is released, that is less than the chemical adsorption. Heat of adsorption is low, that is only -20 to -40. There you will have some 80 to 240. Greater heat of adsorption, chemical adsorption. Lesser is the heat of adsorption, physical adsorption. No appreciable activation energy. Why? As just van der Waals force of attractions are due. Van der Waals force of attraction is developed. To develop van der Waals force of attraction, the bonds present in the adsorbed molecules need not to be broken. So there is no activation energy required. It forms multi-molecular layers on adsorbent surface under high pressure. Under high pressure, what it forms? Multi-molecular layers. Why? Because the van der Waals force of attraction is just going to be developed, and as the distance is going to be increased, the van der Waals force again decreases. It depends upon nature of gas. More easily liquefiable gases are adsorbed easily. Yes or no? Liquefiable gases. If a gas can be liquefied easily, what we can say from that point?
Its molecular mass is high.
Molecular mass is high, sure, or intermolecular force of attractions are high.
Intermolecular force of attraction.
Liquefaction with respect to intermolecular force of attractions is more dominant, right, Faizan? Yes or
Yes,
no?
sir.
So whenever we have more easily liquefiable gases means intermolecular force of attractions high. Intermolecular force of attractions high means what you can say from that point? Greater the intermolecular force of attraction, what you can study from that? That means the molecular motion can be less. If your gas molecules have stronger intermolecular force of attraction, its movement is decreased. If its movement is decreased, it can be easily adsorbed on the surface. If its movement is very fast, it is not easily adsorbed. It depends on the nature of gas. More easily liquefiable gases are adsorbed readily. It decreases with increase in temperature. Physical adsorption, like extent of adsorption with temperature, if you try to plot a graph, extent of adsorption versus temperature. Extent of adsorption versus temperature, you will have this graph. But with the chemical adsorption, you will have a graph, first increases and then decreases. Because chemical adsorption requires activation energy. With increase in temperature, more greatly, the chemical adsorption can occur. Is every point clear so far?
Yes, sir.
Yes, sir.
Yes.
Sir.
Very good. Chemical adsorption or chemisorption. It is caused by chemical bond formation. That is between the adsorbate and the adsorbent, chemical bond is going to be formed. It is highly specific because bonds are going to be formed. Bond formation involves orbital overlapping. So between any two atoms, bond cannot be formed. Yes or no? So bond is formed means there is obviously an orbital overlapping. So highly specific. It is irreversible. It is not said like once the old bonds have been broken and a new bond has been formed with the adsorbent and adsorbate. It is not assurance like we cannot break this new chemical bond and generate the reactants back. So it is not reversible, it is irreversible. Heat of adsorption is high, -80 to -240, as I have told you. Why? Because the extent of adsorption involves the cleavage of bonds and thereby getting a new bond has been developed. New bond formation stabilizes the system greatly, so thereby decrease the energy greatly. Whatever the new bond formed between the adsorbent and adsorbate, that is going to be stronger and thereby amount of energy lost will be high. High activation energy is sometimes needed. Why? As it will enhance the bond cleavage. High activation energy is sometimes needed as it will enhance, or you can simply say as it requires bond cleavages. It forms unimolecular layer because orbital overlapping has been occurring. So unimolecular layer is going to be there. It also depends upon nature of gas. Gases which can react with adsorbents show chemisorption. The gases which can react with adsorbents, they can actually show chemisorption. It first increases, then decreases with temperature. So if you try to plot extent of adsorption versus temperature. Temperature you're taking on the x-axis, extent of adsorption on the y-axis. You will have this type of graph. First it will increase and then it will decrease. Why the temperature increase in temperature increase the extent of adsorption? Because of increase in temperature, the activation energy can be achieved by more number of molecules. Thereby, a new bond can be formed between adsorbate and adsorbent easily. Further increase in temperature can also cleave that new bond form. So that is why it first increases with temperature and then decreases. So these are the major points of discussion. We can just look at all the differences. Physical adsorption, chemical adsorption. Physical adsorption caused by intermolecular van der Waals forces. Chemical adsorption by chemical bond formation. Physical adsorption not specific, chemical adsorption is specific. Physical adsorption is reversible, chemical adsorption is irreversible. Heat of adsorption is low in physical adsorption because just van der Waals attraction. Heat of adsorption is high in chemical adsorption as chemical bond is formed. No appreciable activation energy is involved in physical adsorption. High activation energy is sometimes needed in chemical adsorption because the bonds has to be cleaved. Physical adsorption, it forms multimolecular layers on adsorbent surface under high pressure. Under high pressure, multimolecular layers are going. High pressure means you can imagine the scenario like where you are having some sand. You are taking some sticky substance and you are hitting the wall. This is my wall. You are hitting it. With a low pressure, you hit. Low pressure. Only one layer can be formed, physical adsorption. There is no bond formed. There is no bond formed between the adsorbent and adsorbent, just van der Waals forces. Because of van der Waals forces, one layer can be sticked. The same sand or the same sticky substance, if you hit to the wall greatly, because of applying great pressure, what you can have? Over one layer, the other layer can also be there or not? Yes or no? In the villages, you will
Yes, sir.
see. So whatever you do to the wall with the high pressure, you have to do so that it can stick, so that you can say van der Waals force of attraction will be developed between the next layers and the adsorbent. So it depends. It forms multimolecular layers on adsorbent surface under high pressure, and chemical adsorption forms unimolecular layer. Physical adsorption depends on nature of gas. More easily liquefiable gases, they can develop new intermolecular attraction with the adsorbent. Chemical adsorption means gases which can react with the adsorbent, they will show chemisorption. It decreases with temperature, whereas it first increases and then decreases with temperature. These are the same points of our discussion. Factors affecting adsorption. There are different factors which are affecting the adsorption. What is first one is nature of adsorbents. What type of adsorbent you can consider? Which type of adsorbent you can consider? Nature of adsorbents, nature of adsorbate, effect of temperature, effect of pressure. Effect of pressure you can study with respect to adsorption as them, Freundlich adsorption as them, and Langmuir adsorption as them. Nature of adsorbents. So for adsorbent, we should have more surface area. Nature of adsorbents for solids, we have taken activated charcoal, as I have told you in the previous class also, in the chemical kinetics, like a previous chapter. More is the surface area, more will be the rate of reaction. Same thing here, more is the surface area, more will be the number of unbalanced forces, thereby more will be the respect to adsorption. If you consider a particular solid, for the same solid in the crystalline form or in the chunk form and the same solid in the powdered form, when you consider the powdered form of the solid, it will have more surface area, thereby it will be having more rate of more adsorption happening. Powdered form of activated charcoal, if you consider, there you can have more surface area, because of that more is the adsorption. So whatever the adsorbent you are considering, better consider that adsorbent in the powdered form. That is why powdered form of charcoal will have more adsorption. Adsorbate, what type of adsorbate you have to choose? The adsorbate
More
which can have, yes please,
more liquefiable
more liquefiable. So that means you can consider that adsorbate with respect to critical temperature. Higher the critical temperature, more is the tendency to undergo liquefy. So more is the extent of adsorption. So for solids, you can say adsorption is directly proportional to surface area of adsorbent or free valency of the solid. Nature of adsorbate. For gases, you can consider volume of gases at NTP absorbed by 1 gram of charcoal. You have taken 1 gram of charcoal and you are varying the gases H2, N2, CH4, CO2, HCl, and HCSO2. With respect to critical temperature, you can consider like more is the critical temperature, more is the volume absorbed or not. TC is directly proportional to extent of absorption. Critical temperature is high means the tendency to liquefy is high. If the tendency to liquefy is high, means obviously more will be the extent of absorption. So that you can understand from the critical temperature. If critical temperature is not given to you, if simply directly gases are given to you, like I have given gases like H2, CO2, and SO2, how you can explain? Like SO2 will have more intermolecular force of attraction because it is polar in nature. CO2 non-polar, H2 also non-polar. But in H2 we have 1s overlapping because of that strongest bond. So the instantaneous dipoles developed is also very poor. So H2 will be having very less intermolecular force of attraction. Thereby it will be having lesser, like very high velocities are there, thereby less absorption. CO2 also non-polar, but more absorption when compared to H2. Like whenever the gases, different types of gas are given to you, you have to compare whether the gases given to you are polar gases or non-polar gases from their structures. When the critical temperatures are given to you, directly you can compare. Critical temperature increases, ease of liquefaction increases. Ease of liquefaction increases, obviously extent of absorption increases. With increase in critical temperature, the liquefaction increases. With increase in liquefaction, extent of absorption increases. Like absorption is directly proportional to critical temperature of the gas. Absorption is directly proportional to critical temperature of the gas. Is that point clear?
Yes.
Sir.
Yes, this is the nature of adsorbate for gases. And we can have adsorption from solution also. Like earlier the adsorbate is a gas. So easily liquefiable gases can adsorb more. Now from the solution, adsorption from solution, what you can say? Like I have taken two different solutions and I have added charcoal to both the solutions. One is at concentration C1, other at concentration C2. What happens? Like where the concentration is more, there you can have more adsorption or not. X by M, extent of adsorption is equals to K into C power 1 by N. We'll discuss this graph as well once you have studied with the friendly adsorption theory. Friendly adsorption algorithm, X by M is equals to K into P power 1 by N. Similar to that, we have adsorption from solution also follows. X by M is equals to K into C power 1 by N. From this, you can say X by M is directly proportional to concentration. X by M is directly proportional to C power 1 by N. X by M is directly proportional to C power 0. This is at low pressure. This is at moderate pressure. At a low concentration, because C is a concentration. At a moderate concentration. At a high concentration. Can you understand this? X by M is equals to K into C power 1 by N. From that I have written X by M is directly proportional to C power 1 at low concentration. At low concentration, if you try to increase concentration, the X by M will be directly proportional like a straight line. At a moderate concentration, it will be like X by M is directly proportional to C power 1 by N. It is a curve. At a very high concentration, X by M is directly proportional to C power 0 means it is not depending upon concentration. Why? At a very high concentration, most of the molecules already adsorb on the surface of adsorbents. You have very high concentration, like I have 1 lakh molecules of adsorbate, and I have some 10 surface points on the adsorbents. Let us say 1 lakh molecules I have added, but only 10 surface points available. Out of 1 lakh, 10 molecules will easily adsorb. It doesn't matter whether we have 1 lakh or 1 crore. Once these 10 surface points are occupied, no further adsorption occurs. Can I say like that?
Yes.
Yes or no? So at a very high concentration, it doesn't matter how much concentration it is, adsorption will never occur. At a initial stages, I have 10 surface points, I have added 2 molecules. Adsorption will occur. Extent of adsorption is directly proportional to concentration. I have 10 surface points, I have added 20 molecules. Like moderate concentration is there, x by m directly proportional to C power 1 by n, where it is going to vary in the curve form. So in the low concentration, x by m varies like a straight line. After that, it will be curve. After that, it is independent of the concentration. So I have a curve like this. So this is low concentration straight line. There you have some moderate concentration, you have some curve. At high concentration, you have saturated state. X by m taking concentration. This is happening at a particular temperature T. With the change in temperature, again extent of adsorption changes. As it is a physical adsorption or chemical adsorption, based on that only we can include the effect of temperature. Problems of adsorption from solution will lead to different types of problems, because we can say that initially we have a particular substance of concentration so and so, of volume so and so. We have added some amount of charcoal. Because of addition of charcoal, what happened? The concentration changes. So how many, like what is the amount of solute adsorbed per gram of charcoal? Like that questions can also be framed. Okay, we'll study all that questions and problems as well. Adsorption is directly proportional to concentration of solute in the solution. More is the concentration of the solute, more will be the extent of adsorption. Right? Effect of temperature. As I have told you, like adsorption is a exothermic process. For exothermic process, since delta H is negative, on increasing temperature, adsorption should decrease. On increasing temperature, adsorption to decrease. Physical adsorption decreases with increasing temperature. Chemical adsorption first increases, then decreases with temperature, because chemical adsorption requires activation energy. This is the same point which we have discussed in the examples. The same points, if you study graphically, how you can draw the graphs, x by m versus temperature. At a particular pressure, extent of adsorption will be decreasing if you increase the temperature in a physical adsorption. In a chemical adsorption, it first increases and then decreases. So this is for physical adsorption and this is for chemical adsorption. Is that clear, students? Effect of temperature?
Yes.
Yes. So the next effect is effect of pressure. Okay, this effect of pressure will be leading to 2 different types of isotherms. Like as I was saying, Freundlich adsorptionism, Langmuir adsorptionism. We will discuss that in the next class. Right? Thank you all, everyone. Bye.
Thank you.
Thank you, sir.
Thank you, sir.
Thank you.